The homogeneity of equations. The principle or idea behind the test of homogeneity of equations is that if a physical equation is correct, then every term on both sides of the equation must have the same dimensions. Let's pick an equation that we are familiar with from kinematics, v equals u plus at, where v is the final velocity, u the initial velocity, a the acceleration, and t the time. One way we can check the validity of this or any physical relation, that is an equation, is by entering the correct units for the physical quantities in that equation. In base units, the velocities are meters per second, acceleration is meters per second square, and time is in seconds. The second term on the right-hand side can be reduced to a meter per second. A meter per second added to another meter per second will result in a meter per second. Hence, the equation is said to be homogeneous, which means that the units of every term in the left-hand side and the right-hand side are the same. Another way by which we could verify the equation is by dimensional analysis, or in other words, by confirming its dimensional consistency. Basically, instead of replacing the physical quantities in the equation with its corresponding units like we have done in the previous example, we replace the physical quantity with the letter that represents the dimension. In capitals, L for length, M for mass, T for time, etc. You get the idea. Let's pick a slightly more complicated equation this time. One from kinematics again, S equals ut plus half at squared, where s displacement, u the initial velocity, a the acceleration, and t the time taken or the duration being considered. On the left hand side we have only one term, displacement, which is basically length, thus capital L. On the right hand side we have two terms, and for this equation to be valid, both these terms, that is the first and the second, should effectively reduce to a L, that is length. Only a length can be added to a length to give a length. Let's check that out. Velocity, which is change in displacement divided by time, and distance is length, therefore velocity is L divided by t, and that is multiplied by time. Then acceleration, length divided by time squared, and that is multiplied by time squared. The t's within the two terms cancel out, therefore giving us a length plus length, that is L plus L. And length plus length equals another. There is one term on the left-hand side and two terms on the right-hand side. Every term in the equation has the same dimension, which in this case is capital L, that is the length. The equation is dimensionally consistent because every term on both sides of the equation has the same dimension. The multiplicative factor in this case, the half, is dimensionless, with no unit and can be ignored. An equation can be homogeneous, that is, units tally, therefore dimensionally consistent. However, can still be physically wrong, and that can be due to wrong factors and constants. For an example, we have just seen s equals ut plus half at squared. Had it been written s equals 5 ut plus 10 at squared, the units, hence the dimensions on the left and right, would still tally. The equation would still be homogeneous, dimensionally consistent. However, the factors being unitless and wrong will render the equation physically wrong. To validate an equation which is homogeneous, hence dimensionally consistent, would be to enforce the scientific method of testing the equation by actual controlled experimentation, perhaps by plotting a graph after that or otherwise. Knowing and applying dimensional analysis helps in a few situations. Like in the previous example, it can be used to validate an equation, and we have just seen that. It can also be used in derivation of a formula. Consider the case of obtaining the period t, capital T, of a simple pendulum. The period t is the time taken for one complete oscillation and the dimension is capital T. When you look at the actual physical situation, the various physical quantities that could affect the period t and be in the relation or equation for t are length of the pendulum, dimension capital L, m, mass of the pendulum bob, dimension capital M, g, acceleration due to gravity, dimension is length divided by time squared as it's an acceleration, and theta, angle of displacement from the vertical, and it is dimensionless. Angles are ratios and are measured in radians or degrees, hence unitless. Now, to establish the equation that gives the period t of the pendulum, consider the length L. T could be directly proportional to L or indirectly proportional to L. It could be directly proportional to the square of L or could be indirectly proportional to, say, the fifth root of L. We don't know. And since we do not know and the possibilities are many, we introduce the letter A to denote the power on L. If it was directly proportional to L, then the power will be positive. If indirectly proportional, then it will be negative. And the magnitude of A will give any powers or square roots that's applicable, etc. The same goes for the rest. T could be directly or indirectly proportional to mass m, thus m to the power of b. T could be directly or indirectly proportional to g, thus g to the power of c. T could be directly or indirectly proportional to the angle theta, and because angles are dimensionless, it is ignored. To arrive at the equation, what we have done is that we let the period t to be proportional to each of the other possible physical quantities with an unknown power on each of them. Combining them together results in t directly proportional to the product of L, M, and G with their respective powers. Removing the proportionality symbol, then introduce the constant of proportionality and let that be k. And now the dimensional analysis begins. Dimension of time, capital T, dimension of length, capital L, with a power A, dimension of mass, capital M, with a power B, dimension of acceleration, L divided by T squared with a power C. The constant K is assumed unitless, hence dimensionless, and can be ignored for now. Firstly, simplify by combining the powers of the various letters denoting the physical quantities by using the laws of indices. These two are multiplied, so powers can be added, and bringing the base to the numerator side changes the power to the negative. Next, on the left-hand side, introduce the dimensions that are present on the right but are absent on the left with a power 0. Once again, laws of indices. Note that t has a power of 1. Next, derive equations out of comparing the dimensions on both sides. From comparing L, we get a plus c equals 0. Comparing m, we get b equals 0. Comparing t, negative 2c equals 1. From this equation, evaluate c and put that value of c into this one to get a. The three powers are now known. Put the powers into our equation above. Applying the laws of indices once again, we can simplify the equation to t equals k multiplied by the square root of L divided by g. This is interesting to note, that the two physical quantities m and theta are not in the equation thanks to the power of 0 for m and theta being dimensionless. That proves that the period t is independent of mass of the bob and the angle it is displaced. We have assumed that the constant k is dimensionless. To validate the equation and be physically correct, you will have to carry out experiments, perhaps by plotting a graph after that or otherwise. When this particular experiment was actually carried out, the k was indeed dimensionless and had a value of 2 pi. Therefore, we were correct. Discovering the formula by dimensional analysis will only work if the constants in the equation do not have units, that is, they are dimensionless. If the constants have units and we are unaware of it, then this method would fail. And that is why we need experimentation to prove the validity of the equations.